Hey guys, this is Professor Janacek, and I would like to talk to you about Stokes' theorem. To begin with, we'll let S be a smooth oriented surface in R3 that's bounded by a piecewise smooth closed curve C with orientation that's consistent with S. And we'll let F be a vector field with components F, G, and H, and N be the unit normal vector for that surface S. So our surface is S, it's bounded by the closed curve C, and now we have this vector field on S. According to Stokes' theorem, the line integral of F dotted with dr is equal to the surface integral of the gradient crossed with F and then dotted with that normal vector. This is really very interesting. It is a three-dimensional version of the circulation form of Green's theorem. We can interpret this by saying that the accumulated rotation of the vector field over the surface F, S, equals the net circulation on the boundary of our surface. So again, you can see that connection with Green's theorem in the circulation form. We've just upped it now to 3 dimensions. Let's take a look at an example. We want to evaluate the line integral, and they give us the line integral, using a surface integral. We also have our vector field F is x squared minus y squared for the first component, z squared minus x squared for the second component, and y squared minus z squared for the third component. Our surface is the square bounded by the absolute value of x less than or equal to 1 and the absolute value of y less than or equal to 1. And it's in the plane where x is equal to 0. So hopefully you have an idea of what this surface looks like. So in order to do this, of course, we are going to be using this. Let's go ahead and build it piece by piece rather than putting it all together at once. So let's first take a look at the gradient crossed with F. So remember the cross product. Our first row is I, J, and K. The second row is our gradient, which is the partial with respect to x, the partial with respect to y, and then the partial with respect to z. And the third component are the components of f. So we have x squared minus y squared, z squared minus x squared, and finally y minus z squared, y squared minus z squared. Of course, remembering how you work the gradient, this tells us that we are going to have, let's see, it's going to be the partial with respect to y of y squared minus z squared minus the partial with respect to z of z squared minus x squared. This is the I component minus our j component, which is, let's see, that's the partial with respect to x of y squared minus z squared minus the partial with respect to z of x squared minus y squared. Here's our j component plus k component. Let's see, that will be the partial with respect to x of z squared minus x squared minus the partial with respect to y of x squared minus y squared. And there we go, that's for k. All right, well, let's see, what does this give us? This is 2y minus 2z for I plus, oh wait, actually that'll be minus, oh dear, minus 0 minus 0 for j plus that's actually a negative 2x minus a negative 2y for k, which we can write as 2y minus 2z, 0, and negative 2x plus 2y. Actually, let me turn that around. Let's make that 2y minus 2x, just so I don't lose that negative. All right, so now we have del crossed with f. We're also going to need the unit normal vector. Let's see, the unit normal vector to a square in the plane z equal to 0. Oh, that's pretty simple, right? That's just 0, 0, 1, because we're just going in the perpendicular to that plane, right? Okay, and that plane, of course, is z equal to 0. That means it's in the xy surface. The x and y values are 0, and normal to that would be just in the z direction. Okay, so now we can compute that gradient crossed with f that we just found. Now let's dot that with our normal vector. So that is 2y minus 2z, 0, 2y minus 2x, dotted with 0, 0, 1. And that gives us, oh, let's see, that'll be 0 plus 0 plus 2y minus 2x. So that just gives us 2y minus 2x. And that looks to be our integrand there. All right. So now we're ready to set up this integral. So we're taking the line integral and evaluating it using our surface integral. So that will be, let's see. I know what the integrand will be. Of course, the integrand we just found, that's this right here. But we're going to integrate, let's see, with respect to x and with respect to y. Oh, those both go from -1 to +1. Again, that's because the absolute value of x is less than or equal to 1 and the absolute value of y is less than or equal to 1. And then our integrand 2y minus 2x, and then we'll integrate with respect to our area, or our surface, which, let's see, we could do this in either order. We'll go ahead and write it as dx dy. You'd get the same thing if you change that order. Okay, so what does that give us? If we integrate with respect to x first, we have 2xy minus 2x squared over 2, so that's just x squared. Evaluate that from -1 to 1. Don't forget to write that differential for y. Let's see, evaluating that at 1 for the x values, we have 2y minus 1 minus negative 2y minus 1. So that gives us 2y minus 1 plus 2y plus 1. And that integrand simply becomes 4y. And we're going to integrate with respect to y. That gives us 4y squared over 2, or 2y squared, evaluated from -1 to +1. So that's 2 times 1 minus 2 times 1, which is just 0. So there we go. We end up with 0. Enjoy!